I think we're set tonight. Chapter 8, it's electric. All righty. So as we've talked about a few times tonight, unfortunately the letters don't always match up with the words as you think they would. We talked a little bit last week about the formulas E equals IR, and we're going to see some drawings of how that works and how you, if you know two of the variables, you can calculate the third, and that will be on the exam. There's a couple questions, so it's just a good thing to know, and if you can do simple algebra, if you know one, E equals IR, you can solve for either one, but it'll show, we'll see a little symbol that makes it even easier to do that. So voltage is a water pressure, and I'm gonna just grab this real quick. I don't know who put this here. There's a squirt gun back here. I thought maybe Nelson brought this in. So when I was a kid, you know, these are the kind of squirt guns we had. And I thought when I saw that, well, that's sort of like voltage and water pressure in that you can put water in it, and just with the little pump, you can shoot it 10 feet, but it doesn't hurt anything. There's not a lot of water. Well, that's sort of the voltage idea, is you've got lots of pressure pushing that water through, but the current is sort of the quantity. So if I had a fire hose and put lots of water through to shoot at 10 feet, you're going to get all that pressure, and it's going to be a lot stronger, is a way to think about it. And that's why in the wintertime, if you have static electricity, that voltage is really high. It can be 10, 20,000 volts, even more, but there's no current to it. There's no quantity of the voltage, which we measure in amperage, or the I in this case. And then resistance is the drag, and some illustrations to help illustrate that. And resistors and resistance, that's kind of nice. It all matches up. It just is like if you think about a water hose nozzle, it just restricts it down and reduces the flow. So Nelson, anything on there we ought to talk about? These are actually the questions on the exam again with the letters on there. Well,
we've mentioned before, in fact, Jim Cook mentioned it a couple weeks ago, but it's really important to understand that voltage is potential. It's the availability of force. It's not force actually acting on anything. So you can measure voltage with a meter. You can, like you would with water, you could hook up a pressure meter to see how much water pressure is there, even though no water is flowing. Whereas current is actually the quantity of that water flowing, or the quantity of those electrons that are flowing through the circuit.
Yeah, and to that extent, when we use the volt ohm meter, which Nelson has there, when we measure voltage, we'll put a probe on both sides, on the plus and the minus. But to measure current, we're going to have to put it in series so that it goes, so the current actually goes through the meter, and that way we can measure the amperage, which is a little different. There may be an illustration in here that shows that even, so.
So a common thing people starting out might ask, okay, so let's say the wall outlet in my house, I want to know how many volts it is, and I want to know what amperage circuit that is. So I set my meter to volts, I plug the probes into the outlet, and I can see how many volts are there. Well, is it a 15 amp circuit or is it a 20 amp circuit? Let's go to the amps mode and put the probes in and find out what amperage it is. Not the way it works.
Yeah.
Because at that point, as much current as possible will flow through your meter and damage it.
Yeah. Yeah, those meters aren't really designed, they're designed for low current. I'm not sure what the maximum current is, but it might even be milliamps rather than even a full amp. So just parts of an amp, because they're designed for electronic circuits and the small current that you'd find there versus household current.
The other thing, I'll talk about this more when we get to components, but everything has resistance. Even components that aren't designed to be resistors, they all have a small amount of parasitic resistance. Even wire does.
Yeah, the longer your wire is, the more resistance it has.
Sure.
And we talked about antennas and coax cable, and so copper is a very good conductor. Gold is an excellent conductor. Unfortunately, it's very expensive. Aluminum conducts electricity, but it's not a great conductor. And so what sometimes we do is we put a coating or plating on top of the wire. So some antennas will actually be steel wire antennas now, because it likes the strength of steel, but steel's a fair conductor, not a great conductor. And then we'll copper coat that steel, and that ends up being a pretty nice antenna. And we can do the same with aluminum. In fact, I just read that for this, I think 2024 National Electrical Code, they've approved 10 amp circuits
With 16 gauge
with
wire.
with 16 gauge wire. And what they're doing is, because aluminum's so weak, they're copper plating that. And copper's not a very strong element itself, but it does make it a little bit stronger for LED lighting and some of the low current demand kinds of things, and to help cost as well. So, and Nelson, you may have been telling me that last week about the NEC change on that. So. All right, so direct current. So we think of batteries as being direct current. The battery in your automobile is direct current DC, flows in one direction, and kind of a battery showing the flow of the water, where alternating current changes direction depending on the frequency. So Nelson mentioned the 60, I called it 60 cycle. I called it cycles for a long. The Hertz, need to give Mr. Hertz his due, so we call it Hertz today. And anyway, changes direction. And so that's hence the name alternating current. And then impedance is opposition to that flow. So it's the resistance to that. And it goes through, there's 2 questions that'll be on the exam as well. Nelson, anything you want to add to that? Again, I'm trying to keep it a little top level, but okay. This is probably intuitive. In fact, we talked about that just a little bit ago. Some metals, or all metals, most metals are good conductors versus an insulator which resists the electricity. Things like plastic and glass, porcelain, vinyl are typically really good insulators. But that insulator is really important. Thinking about coax, just the type of insulator that separates that center conductor from the braid or the shield that goes around it makes a lot of difference.
Oh, yeah.
And you can buy, and I think Adam last week talked about an air insulator, which is typically a very good insulator. Some of the FM radio stations, in fact, our repeater will use an air insulated coax, and where it's just air between the center conductor and the outside. Certainly if that air is humid, and it can vary a little bit, but typically it's a very good insulator.
A lot of times what they'll do is they'll actually inject the gas into those lines to keep the
moisture out. I did not know that. Yeah.
They'll pressurize it with
Yep.
Nitrogen?
nitrogen or something like that. So
Yep. Good. Thanks, Michael.
I learned all this stuff when I was very little because my parents had an electric fence. We had horses.
Oh yeah.
So,
Yeah.
So did you notice when it's humid that you actually could see an arc between the wire and the post that it was attached to? At least I had that problem once in a while where it
Yeah.
arced right across the insulator.
Yeah.
we never really had that problem because the posts were wood too, most of them. We did have a couple metal posts, but we were using standard insulators on them, so they had seen it off, and they had the little plastic fin around them to give them further distance from.
Yeah.
That's good.
Yeah.
It was fun to let the weeds grow tall, because the weeds had just enough moisture in them. They'd hit that. We had an electric fence as well for horses, and it would, zap the. Yeah. And as kids, we learned to stay down before you got up too fast when you were crawling under it, because it hit you on the back, and you feel it.
Spent much of my childhood keeping the weeds trimmed underneath my electric fence. This is, okay, I'll speak to this. This is a fantastic diagram. And this has been going around the internet, so Michael, you could even show this, where this person here representing voltage, that's the force pushing the electrons through the conductor. Amp, he's the guy actually being pushed. He's the guy moving, doing the work. And this guy here, resistance, he's the one trying to keep this guy from doing his job. He's trying to keep these electrons from moving through that conductor.
So if you think of the water example, again, he's constricting the pipe so it's smaller, so as you can imagine, less water gets through, and gauges of wire are the same thing. When you've got a thin gauge, 18 or 20 gauge wire, it just can let high voltage through, but it can't let a lot of current through, versus a 12 gauge household wire, 10, 8, something very, very large.
Actually, I'm going to go off on a tangent a little bit with that, because that's a great example. With a lot of components, wire included, there are voltage ratings and current ratings. Even if they're not published, there's just a common sense to what this can carry. The thickness of the conductor really tells you how much current is safe to carry through this wire. And the resistance of the insulation, being its thickness, its construction, its condition, and so forth, really dictates what the maximum voltage is that you can put through a conductor like this.
Right.
So these components don't really care what voltage they are, so long as you don't exceed a certain rating where you arc over or short out or whatnot. But this little thin test lead really can only carry a tiny amount of current just because the conductor inside is so thin.
Yeah, I mean, a lot of fuses are made just of thin pieces of metal that melt when they get over the proper amperage.
Great example. And I'll talk about this a little bit more too. Going back to our water analogy, at home I have a home water softener. But I also have some faucets that are not connected to the water softener. But my water softener, it's been there for probably 40, 50 years, and it's getting plugged up inside. Now, if I just open one faucet in the house that has soft water, I get all the water I need, no problem. But the minute I open a second faucet, I don't get much water out of either one of them, because that water softener is acting like a resistor. It's plugged up inside, so if I'm not expecting a lot of flow, I can get enough pressure at one faucet because there's not that much flow through the water softener. But when I have two faucets open, now I'm expecting a lot more water to flow. But because of that resistance, it restricts how much water can flow, and as a result, I lose pressure at the faucets.
Right, you're dividing your pressure across multiple components over.
Now, if I open a faucet that's ahead of the water softener, not soft water, that'll have all the pressure I need no matter what happens with the rest of the faucets in the house.
So Ohm laws relating different values of voltage, current, and resistance in a circuit, as the slide says there. E, again, the voltage, I, the current, R, the resistance. So the formula, the way I remember it, is E equals IR. And as the book explains, if you sort of imagine this eye chart with the E on top, the big E that we always see in the eye charts in a triangle, for whichever one you want to solve, you just cover it up. So if you want to solve for I, you cover that up, and it's E divided by R, and the same way, just like that. And we'll do that with power in just a moment too. We'll see something very similar to that. And here's the breakdown of those. Just a little visual representation in a memory aid, if you will.
If you remember there's the two triangles, that will help you on the test. So.
And they're really, it's something you really use. Some of the things you don't really use, but I find myself using, these all the time. And so it's a good thing to know that rather than just memorize the particular, answer to the exam.
Where I struggle is sometimes, if I'm in a situation, remembering which of the two formulas is appropriate for what I'm doing. I struggle with that. One thing I find helpful is, if I have a ballpark idea of what to expect for an answer, I run the formula, and if I don't get an answer that's in the ballpark, then I know I've done something wrong. If I calculated the resistance of this wire and I got 5,000 ohms, I'm doing something wrong because that's not realistic.
Right.
So again, these are just examples of the same thing. So what is a voltage? So we're solving for voltage. And so cover that up, and I divided by R, 2 amps divided by resistance, 10 ohms is 20 volts. And again, another example down there, so. Forgot about the pink fingernails there. Okay. And then finally, resistance example, so one for all three. But again, there's 2 for each value there, so that's 6 questions. So boy, do I remember 6 answers or just remember E equals IR? And you can write on the exam. I brought a piece of scrap paper with me for my tests, for all the tests. And some of the things, I just wrote down the formula. Even though I knew it, it just was easier to look at the piece of paper, so feel free to do that. And it helped me, I mean, these are pretty simple, but still, just use the paper to your advantage.
Right. I'm pretty good with formulas, so this should be good.
And this is very similar, but this is the power law. So this relationship is a relationship between power, voltage, and current. And as we'll see in a minute, the power is measured in watts. Right there it is, actually. And as in voltage, E equals IR, power equals E times I.
Oh, yeah, I got this.
Yeah.
Just remember pi
Yep.
for the triangle.
Got your pie chart there with a P on top.
I know I'm remembering it wrong, but I just got W times VA memorized.
Mm-hmm.
Again, some examples for each. There we go. Does it all make sense, Will? I mean, it's just simple division and multiplication, so.
Yeah, the biggest thing is remembering where to put everything, but that shouldn't be too hard. The watts one I know I've got, because I forget what I was doing, but I was doing a lot of voltage time amperage calculations.
Yeah, if you could just remember that E is volts and I is amps, and R is easier because it's resistance measured in ohms. And then I always thought of the I chart, always had the big E at the top. This is how I remembered the E equals IR. And then the pie chart, which Michael said, that's a good, good way to do that one as well for the power chart, power law. So decibels probably took me longer to sort of cement in my mind than the others, just because it's on the logarithmic scale and it gets in multiples of 10. And for the exam, I probably, the things I remember, I guess, is that a 3 dB change doubles it, and then it takes 6 dBs to make an S unit increase. I think we're going to see some of that in a minute. And the reason we do that is that the values are they swing so huge. I mean, lots of values are big. In this case, they go from very, very small to gigantic, so from 1 to 1,000,000. So you end up with really huge numbers. So we use the logarithmic scale just to make them a little easier to understand and to make them very comparable. So in the FT8 that we looked at last week, we were getting signal strength, and it's always relative to something else. When we talked about antennas, we talked about an isotropic antenna, that a Yagi had so much gain over something. So dBs tend to compare something with something else. In our antenna example, we recognized that a Yagi antenna, that was the tape rule one that I brought, that had elements of reflectors and directors and an active element, had gain over something else. It had 6 dB gain or something. So it's just a relative measurement compared to something else. So in that example, it was compared to just an ordinary wire antenna. We called it an isotropic antenna. So again, and we use a lot of negative dBs as well, so don't get tripped up by that. But last week when the stations were coming in, we had some coming in really strong, and it was reporting 5 or 6 dB, which is for a weak signal propagation like FT8 is really a strong signal. One of the great things about FT8 is it does very well with weak signal. It can pick the ratio of signal to noise can just be right in the noise, and the computer can kind of pick that out. So I get a minus -8, -10 signal, which is a pretty good signal for FT8. When I get to -20, and now I'm 20 times, I mean, it's a huge difference. I can still pick it out, but it's much weaker. And I think -24 is about as low as FT8 gets dB, is just to give you some practical examples of why we're learning dB and how you might use that.
I'll add to that a little bit too. The reason that a logarithmic scale is helpful is, in this example, 5 watts to 10 watts, that's a big difference, that's a big change. So what about 5,000 watts to 10,000 watts? Well, that's an extra 5,000 watts. That should be a humongous difference. Nope. Still 3 dB. If you're receiving a station and you're on the fringe of that station's coverage and they double their power, you'll notice a small improvement in signal quality. If you're listening to a closed station running 5 watts and they go to 10 watts, it'll sound a little better. If you're listening to a distant station running 5,000 watts and then they go to 10,000 watts, still sounds a little bit better. So that's where putting an amplifier on your station is helpful, but it also, there's the law of diminishing returns. So going from 5 watts to 10 watts is great. If you want to improve your signal, you double that to 20 watts, you double it to 40, to 80, to 160. Let's say you're at 100 watts, well now you've got to go to 200 watts for even a small noticeable difference. 1,000 watts, you got to go to 2,000 watts. Now that's outside what hams can run. But that's where big stations, big amplifiers can get pretty silly pretty quick.
Yeah.
Other thing about logarithmic scales is a 10 times change, like 10 to 100, 1,000 to 10,000, we often call that an order of magnitude.
Yeah.
So if someone says that's an order of magnitude better, and it's 10 times better.
So on your transceiver or receiver, or even on your SDR, it'll have a signal strength meter. We call them S meters. And the usual scale is 1 to 9. And then once you get to 9, it usually changes color, goes to red, and then you get a 10 and maybe a 20 and so forth. But if you have a signal up to S9s, that's a really good, I mean, S9 is a really good signal. You get to 10 and 20 is this sort of icing that doesn't do you much good. But if your signal strength drops down to an S8 or an S7, you can hardly tell. I mean, when you get down to 2 to 1, I mean, maybe you start to lose people in the noise, just the normal background, the noise level we call it. But there's just not a lot of, I mean, there's some, clearly from S1 to S9, there's quite a bit of difference. But if you go S7 to S9, not a big difference. Well, in Nelson's example, if you were running 5,000 watts and you got an S7, you'd go to 10,000, I'd double it. I'm not even to S8 yet. I'd have to double that again, go to 20,000. So I'd have to go from 5 to 20 to go 1 S unit. To go from 7 to 8 would take, in that particular example, 5,000, I'd have to go to 20. I double the 5 to get the 10, then I double the 10 to get the 20. That's 1 S unit. So it's just like, gets silly pretty fast was your expression. I think that's a good example. So
Last summer, I was talking to Dale Reynolds, and he was explaining to me that he was working on one of the 100,000 watt stations, but they had turned the power down so the guys can get up and work on the antennas. And he was explaining to me to go from 50,000 to 100,000, they only gain 7 miles.
Wow.
But the difference is they can penetrate walls better with the FM signal. Well, he's like, yeah, you only gain 7 miles doubling from 50,000 to 100,000. And I would think, okay, maybe 15, 20 miles. But he's like, yeah, 7 is all you get.
And you have to look at, is the cost of the electricity that you're putting into the system worth it for that extra 7 miles
Right.
of coverage?
Yeah.
some of it's just marketing. If you get a handheld transceiver, most of them are about 5 watts. And they'll do less than that. They'll do 2.5 or 1. Once in a while, someone will go, oh, ours is 6 watts, or maybe 8 watts. You see some up to 8 watts. Well, to go from 5 to 8 is just almost nothing. And it's just,
Well, it sure eats up batteries.
yeah. Yep. Probably for me, the easiest thing was to know that to double something is a 3 dB change, and to have it is a negative 3 dB. If you can kind of get that, you can from there go to about wherever you want to get to. That's how I usually think of doubling or having power.
When you get into looking at your whole system, and you've got a transmitter putting out X amount of power, you've got an amplifier increasing that power, you've got coax, which is reducing your power, and you've got an antenna which has gain in a certain direction, it's easy to calculate how much power you're actually putting out into the air, your effective radiated power. It's easy to calculate that when all of those intermediate steps are all rated in decibels. So if your coax has, for a certain length, a certain frequency, has 3 dB of loss, it's losing half its power, it's easy to just literally take how much power you're putting out minus your coax loss plus your antenna gain and get an answer. It's just basic arithmetic.
Yeah.
Because this logarithmic scale makes that possible.
Yep. All right. Just some practical use of applying Ohm's law or the power law. It's not really different than what we've looked at, but just we sort of were suggesting that different gauges of wire have different capacities, and we can calculate all that. Anything there, Nelson or Michael, that we ought to? So this idea over here, especially if you're, so this is talking about a power supply. So very seldom does, especially an HF transceiver, have a power supply built in. So even 2-meter rigs, you'll have a separate power supply, or you'll connect it to your automobile. So typically, if you've got a 50-watt mobile transceiver, you wouldn't want to plug that into the cigarette lighter, because a cigarette lighter doesn't deliver that many. I don't know what a cigarette lighter delivers in amps, but it's about 3 amps, yeah. So it's a lot less than what a 50-watt transceiver.
You can pull 12 amps through it for a very short time.
Until the fuse blows.
Or you melt the wire.
Yeah. Well, hopefully the fuse will blow before you melt the wire, but absolutely.
I say it's, what, 9 volts at, is it 9 volts or is it 12 volts for the cigarette lighter?
12, yeah, it would be 12 volt, yeah.
Only 36 watts, so.
Yep.
I'll expand on this example here a little bit where it says short heavy gauge wires are used for a transceiver's DC power connection. When you're looking at, especially with wire, when you're looking at the whole system, whether you're wiring a house, building a Go kit, putting a transceiver in your car, etc., you want to look at how much loss is acceptable. You could say, well, I can't have any loss whatsoever. Well, reality is all wires have some loss. You have to accept some loss. And quite often that number actually is in the specs for the radio. So maybe a radio spec specifies that it'll give full power output down to 12.2 volts, for instance. And your power supply or your automobile puts out 13.8. Then you can calculate how much loss is acceptable. And from that you can figure out what gauge wire is realistic. Maybe you find that you need an 8 gauge or 10 gauge wire, which is fairly heavy. I don't have a good example of that. This here is probably 16 or 18. Now over a short distance, maybe that's acceptable. I've made up little power adapters going from a power pole to a Molex or something, and maybe I'm pulling 20 amps through this 16 gauge wire, because over that short distance, that little bit of resistance I've decided is acceptable. But I wouldn't want to run my transceiver through 10 feet of that wire. Then I'm going to go up to a higher gauge wire. Same thing in a house. Let's say you're putting in a 20 amp circuit for your radio, AC wall outlet, and it's 30 feet from your breaker panel. You run a 12 gauge wire, 20 amp circuit, no problem. Let's say it's 400 feet from your breaker panel. Maybe go out to 10 gauge wire just so that that voltage drop at full current is still within spec for what your system needs.
All right, talking about electrical instruments to measure voltage, a voltmeter, or sometimes we call them VOMs or volt ohm meters, because typically they do multiple things. Nelson's got one there. A lot of them are digital. Remember the old Simpson, we used to use a Simpson needle, which were wonderful volt ohm meters, but in some of them are really quite inexpensive. This is LCR. It'll read, in fact, I'm going to put that over here. I'm going to have you measure some components here when we get into the components. But it'll do transistors, capacitors, inductors, and it'll read in henries and ohms, and pretty interesting. It'll can tell you whether the transistor is NPN or PNP. We're going to look at that here in just a moment as well. So I guess this is important here, not I guess, it is important. Voltmeter is connected in parallel to a component to measure voltage. So for voltage, we're almost always doing something parallel versus the current or the amperage where we're in series and reading it, through the component. Anything else there, Nelson, you want to add?
Yeah, I'll talk about this some more. We keep saying that to measure current, the current has to flow through your meter. So let's look at some practical examples of what that looks like. The first is, in any given circuit, from source through the load that's being applied, through other components, back to the source, it doesn't matter where in that circuit you measure current, because the current is equal throughout that whole section of the circuit. Now, if you're looking at a small circuit within a bigger device, the current's not necessarily equal elsewhere in the device, but within that series circuit, it does not matter where you measure current. So to actually measure it, it depends on the characteristics of the circuit. You can take a meter like this, and it actually has a separate spot right on the face of the meter for measuring current. So I'll take this red lead, hook it up to my current source. Let's say it's a battery. So I'll hook this up to battery positive. It's flowing through the meter. We'll put it in amps mode. And I'll take the negative lead and put it back in the circuit so it can continue on through our light bulb or our radio or whatever it is that we're measuring. Or there's various types of clamp meters. In this case, you don't have to open the circuit. You don't have to break the wire.
Yeah, just hanging off the wire, right?
Yep. This works great for alternating current, because what you're actually doing here is making a transformer, and we'll talk about that in the next chapter. But this becomes the secondary of a transformer, and that's why if you look at these, quite often they actually have
Metal contacts.
little laminations.
Oh, okay.
There's a whole series of plates all stacked together, just like you find in a transformer. So that's real easy with alternating current. So here's one that the current flowing through the circuit literally directly drives the needle in this meter. There's no batteries in this.
Right, there's a little magnetic coil on there.
Mm-hmm.
Right, it's induction, so it's induced. I don't know
Yes.
if we talked about induction yet or not, but
Or same with a meter like this, it does the same thing. You can do this with direct current, but it's a different process. Because with alternating current, the current flowing through this wire is constantly changing direction and is creating an alternating magnetic field. The magnetic field is building and collapsing and building and collapsing. And that constant change is real easy to measure with something like this.
Yeah, it's the same way a generator works.
But with direct current, the current's always flowing in the same direction, and it creates a magnetic field. But as long as the current is steady, that magnetic field is steady. It doesn't change. And so you can't pick it up via induction through a transformer. Instead, meters that clamp around a wire like this that measure direct current use what's called a Hall effect. And that's where you're actually measuring the strength of that static magnetic field. A poor man's way to do that is to actually take a compass, a regular magnetic compass. It's even better if it's a compass that you don't care about, because you can actually remagnetize or demagnetize the compass in the process. But if you wanted to see if current is flowing through this wire, just put a compass up next to it, and if you see deflection of the needle, current's flowing. In fact, for very, very large currents, like you might have for the starter on an automobile, I've got a little meter that's basically a form of a compass you put over the wire, and it's got a needle that will have deflection based on how much current is flowing through that wire. And I just used that the other day to diagnose a bad starter on the car. Those are not as common, though. The vast majority of the times that you see a clamp like this, it's just AC. Another way is to measure direct current is to use a current shunt. And what that is a very low value resistor, which like I said, even a piece of wire is a resistor. So as long as you know what the exact resistance is, you can go back to Ohm's law and calculate current. So in my Go kit at home, I've got a shunt hooked in series with the power going into my radio, and then a little digital meter hooked up to that shunt that's actually measuring the voltage across that shunt. So that's another way to measure current. Now when you're hooking up wires in series with your meter like this, that's actually what's happening inside this meter. If you took this meter apart, you'd see a big heavy, about a 16 or 14 gauge wire inside the meter. And what that is a precisely calibrated resistor. Now the consequence of that is, no matter what way you're measuring current in a circuit, a little bit of that current has to go through your meter, and it's actually being lost in the measurement process. So when you clamp this around a circuit, you need a little bit of power to make that needle move. And so that is actually stealing a tiny amount of power in the circuit that it's measuring. For in most cases, that is negligible, not worth worrying about. But if you're talking about very small currents, that parasitic draw can be a problem. Just something to keep in mind. And it says there, sorry, one last thing. It says there, be careful what voltage that you measure with your meter. Any modern meter has a CAT rating. So this says CAT 3, 600 volts. And you can look up what the specs are for the various categories. There's CAT 1 through CAT 4. Basically, the higher the category, the safer the meter is at higher voltages. Even though this is only rated to 600 volts, if I put this across a 1,000 volt source, I'm still pretty confident that it's not going to blow up or harm me in some way. But it's only rated to 600 volts, so I want to be reasonably sure that what I'm measuring is 600 volts or less. If you need to measure higher voltages, there are various ways to do that. Here's the extreme. This is a 40,000 volt probe. And I forgot the meter that it hooks into, but I've got a 6 kV and a 40 kV probe. So you literally can stand way back here. And where do we find voltages like that in ham radio? A few places. We talked about the world of broadcasting. In big transmitters, you can find some pretty high voltages. Even in little tube-type radios, vacuum tube radios, which I'll talk about in the next chapter, it's not uncommon to have several hundred volts on the plate of a vacuum tube, even into the thousands on some transmitters. And so that's where a big probe like this actually is helpful. Televisions, old TVs, CRTs, so the bigger ones, they ran 26,000 volts on the horizontal.
Yeah, I've heard those can be quite dangerous if you're not aware of what's going on.
Sure.
So I was 15 years old when I got my first out-of-house paying job, and it was for a TV repair shop because I loved electronics, and back then we had big cathode ray tubes for TVs because blown glass, and the big power supplies that Nelson was talking about. And the thing I was going to mention under the caption of high voltages is to remember that capacitors store voltage. So even when something's unplugged, that capacitor can have, particularly if it's going through a transformer, so you go, well, I only have 120 volts. Well, through a transformer, I may step that voltage up, that capacitor may store that, and you could have sometimes very, very high voltage in the circuit via the capacitor, even after the unit's unplugged. Well, we should never have been doing this, but I was only 15. So these television tubes had big high voltage cables coming from the power supply that went into the back of the glass tube. And they had sort of a rubber suction cup around it to hold that probe into the tube. And we'd ground a big old screwdriver. We'd ground the screwdriver after it was unplugged, and we stick it up into there just to discharge the capacitor, and it would always just spark like crazy. Your high voltage probe may have been a better way to do that, but
Honestly, though, for TVs, that is proper procedure. You want to ground that.
Ground that, yep.
Yeah.
But anyway, so.
Or in broadcasting, they have what they call a chicken stick. You open the cabinet door and you chew chicken and stick your fingers in there, so you stick or sometimes they call it a Jesus stick, because if you don't use it, that's who you'll meet. and you'll use that. It's got a hook on the end, so you can ground out the parts of the circuit that might store voltage, just to make sure that it's all discharged.
Yeah.
Yeah, I was watching a guy on YouTube just recently. He was looking at a cheap Chinese-made, what is it? It was a light of some kind, but I'd use the capacitor as a voltage smoothing.
Yeah.
Um,
Sometimes we use that to filter AC to make it DC, and we'll run it through a capacitor to the smoothing that you're talking about. or-
Yeah, and so the capacitor didn't have any way to discharge itself, so as soon as the light bulb was unscrewed, it was a
Yep.
very dangerous effect.
Yeah.
Mm-hmm.
Yep. Well, we got our ahead of ourselves maybe a little bit, but the ammeter that Nelson talked about, it's sometimes built into a regular volt ohm meter. That would be properly called a multimeter as well, volt ohm meter, because it does multiple things, hence the name
That's
multi.
what I heard from, was the multimeter.
Yeah, multimeter, yep. Sometimes you see VOM, volt ohm meter,
Yeah.
same thing.
There are some meters that truly are single purpose, like this. This is just an ammeter.
Mhm.
And that's kind of more of an older thing. In the old days, those often were separate components. One thing I'll say briefly about measuring resistance is to measure resistance, your meter needs a little current flow. Like with measuring amps and even voltage, there's a little parasitic element to your meter. So the reason that you have to be careful with that is some components, especially with older meters, when you're measuring resistance, may not be able to handle the voltage that the meter uses to measure resistance.
Right, the meter puts out its own voltage. to
Right.
measure resistance.
Now, in most cases, modern meters, they put out a very small voltage, and there's some resistance built into the meter to protect the component that you're measuring. But you get an older meter, a cheaper meter, it might have a 9-volt battery in it, and it's actually putting 9 volts right on those probes. You go to measure a little transistor that can't handle that voltage.
Yeah. I blow more than one transistor trying to, and a volt ohm meter doesn't tell you a lot about the transistor, but if all you're trying to determine if it's working or not, if it's open or closed, you can put an ohm meter on 2 leads and begin to do that, but certainly can do too much. We're going to, when we look at components, we'll have you measure some resistors and some other components too. I mean, there's really nothing more to that other than to say that you want to make, so you never want to measure, never is a long time, but normally you would always turn the component off, the device off before you measured the resistance. Unlike voltage where you need to have it on, if you're going to measure a resistor, you'd always want to make sure that it didn't have electricity, mostly because the sensitivity of the meter is such that a voltage induced to the meter could ruin the meter. So if you're going to measure ohms, you definitely want to make sure the device is off. And it's sometimes difficult to measure the true resistance of a resistor in the circuit because there's other things attached to it that'll affect that. And again, if we have time, we'll do something simple like we'll put a couple resistors in series and see how that looks as compared to 2 resistors parallel to each other, and we'll get some different results. This is just saying that as a capacitor discharges, so we've talked a lot about capacitors storing voltage. Eventually, I mean, they're not perfect, so eventually that'll be depleted. But as that happens, the resistance goes up. And if you put an ohm meter, I'm not quite sure how I guess if the capacitor were discharged, simply putting a meter on the capacitor would add some voltage to that, and then the resistance would go up.
Yeah, that's actually a quick and dirty way to test a capacitor. In the practical sense, this actually is something that I do when you're working with these larger electrolytic capacitors, the type that are often used to filter the output of a power supply. Because the meter in ohms mode produces a small voltage, when you take a capacitor like this, at the moment, it has a great ability to accept a charge because it is fully discharged right now. So if you put a voltage across it, a large current will flow through this capacitor. Now I'll go on a tangent here a little bit. If you really want to get philosophical with somebody, ask them whether or not current truly flows through a capacitor. I'll leave that for a different day. In the physical sense, I suppose it doesn't really, but from the practical sense, let's just say that current will flow through a capacitor. Because your meter is putting out a small voltage, when you first, I measure the resistance here, when you first apply that voltage, by means of the meter to this capacitor, a large amount of current will be able to flow, so the meter will tell you that there's very little resistance. But as that charge builds up in the capacitor,
It'll accept less current.
right,
So it'll show a higher resistance as it goes.
so right now we're at, oh, maybe this is a bad capacitor. Shorting out the
Yeah, yeah.
idiots right here. Let's try this again. There we go.
It was just full already.
Yep. So that started out pretty close to 1 ohm, and now we're up into kilo ohms. It's 18K, 20K, 21K, 23K, 24K.
Oh, yeah. Well, that makes sense though.
Yep. So that's just a really quick way to see if this capacitor does still have the ability to store some kind of a charge. Now, Larry's meter here actually has a capacitance function on it, so it'll measure the actual value of this capacitor. That effect is true for all capacitors, but smaller ones, like we'll talk about these in the next chapter, their capacity is so tiny that it's just not practical to measure that rise.
I assume they just get fold up and then
That's where you
act
can,
like a resistor.
and that's where you can get an LCR device, where you can put one of those little discs, it's probably a picofarad, it's probably measured in picofarads, it's just very, very small, but that'll at least tell you if it's functional and what the value is. And just, I think we've talked about all that. Again, these are some things that are really useful, and you probably just need to memorize them, and probably not a surprise because those same prefixes are used in lots of different industries and things. Giga, a billion, mega, kilo, milli, and so that's on the big side, large size, and then on the diminishing side are the millis, micros, nanos, and picos. And you will have some questions where you have to convert one to the other. So there's one of the questions there, 1,000 volts is equal to a kilovolt. And sometimes you'll just see K, and we know that that means kilovolt. Kilocycles.
I do a lot in meters and kilometers, so the K is really easy. Micro.
And again, here's some examples where we're taking one to the other. Sometimes on paper, if I forget, I just start adding zeros. So I know K's 3 zeros, and then you just go up from there, add 3 more zeros, 3 more zeros. And
Or subtract 3 zeros.
yeah, or subtract, right, Michael, yeah, exactly, if you're going the other way. Yep.
The small one's gonna be the one that I have to remember.
Yeah. Micro, milli, unity.
Well, millimeter would be easy, because that's a thousandth of a meter. The micro, nano, and pico is the one I'm gonna have a hard time remembering.
Just remember, unity is 0,
Yeah, yeah.
or base. Unity gain. I use those terms now with audio, and I'm teaching young kids, and they have no clue. Analog world, it meant something. Digital world, it doesn't really mean anything. It's just a line.
Oops. Talking about batteries, carbon zinc, as a kid, that's always the batteries we had. Didn't have alkaline batteries yet. Now there's all sorts of chemistries that are used. I have nickel iron phosphate. Is that the right name that I had here last week? And it's just a compact set of chemistry that is able to have a large current capacity. So it was a 20 ampere hour. So theoretically, I could pull 20 amps out of something for an hour. But there is something called a discharge rate. So even though it can do that over time, you can't always pull it out in as short amount of time as you want. So if I wanted to do 40 amps in a half hour, I probably couldn't do that because it just couldn't extract that amount of current in a short amount of time.
Yeah, in fact, I'll touch on that briefly. I'm surprised this was not in the book because to me this is important to understand. The book will tell you probably on the next slide, this is a 7 amp hour battery right here. Maybe it's 8, maybe it's 9, but in my world, this is a 7 amp hour battery.
5. It's on the, right next to 12 volts on the thing, 5 amp hour.
Okay. So that can supply 5 amps for 1 hour.
Right.
No. Theoretically, that rate is assuming that it's supplying the load for 20 hours.
Oh, okay. That's how they got the number?
Mm-hmm. So it's a little bit of trickery there, but at least it's consistent industry-wide. All these rechargeable batteries, that amp hour rate is assuming a 20-hour discharge.
Yep.
Now, of course, it's not on the,
Oh, that's the TV doing that.
yeah, that's the TV.
That's the first time I've seen that.
Me too.
Nope, tap it again. Not in this session. It's asking if you want to keep that.
Oh, okay, thanks.
Yeah.
If you're actually discharging this over 1 hour, it's somewhat less than 5, and the spec sheet for the battery will tell you that. But to me, I think that's important to understand, because if you're expecting that to supply a 5 amp load, it won't go an hour,
Right.
because the battery chemistry just can't keep up.
And the other issue was some of the older technologies, in particular, that's a gas mat battery there, but just in a regular lead acid battery, it's only recommended that you discharge them to a certain level, so you don't take them down to 0. You may
Yes.
take them down to 60% or some, relatively high number.
You can damage the chemistry in that.
Yeah, exactly right. And the other thing you have to look to is what's the minimum voltage that the radio wants. So if it's a 12-volt radio, it really wants 13 volts, so you can maybe do 11.8 or something just barely under 12. But as soon as you drop that, even though theoretically there's more capacity in the battery, the radio just won't run because it wants a minimum voltage there.
It's typically known, a lead acid battery, if you take it down to 50%, you've killed the battery.
Yeah, yeah.
So, that's where you gotta get nickel iron batteries. You can drain them down to 0,
Oops.
I wish those were more of a thing.
but they're just like the ones I have are, they're 50 pounds a piece
Yeah.
for 1.2 volts.
So we really talked about this just a second ago and to calculate the hours. The thing we probably didn't mention is that typically the rating of the transceiver is rated at the most power that it would require. So that would be on transmit. It takes a lot more power on transmit than it would on receive. So this idea is, well, if I'm going to calculate that, chances are, if it's our 20 ampere hour battery, I'm not going to be transmitting for 20 hours. And so this thought is, well, maybe if I transmit for 30% of the time, and it could be that my listening time is 70%, it may only require an amp or two. Usually receivers require very little power compared to the transmitter. So to estimate that 20 amp transceiver, may run for 5 or 6 hours because I'm only transmitting for just a fraction of the time, and that's all that's trying to capture.